Good morning, everybody. This is Sean Wallace. I'd like to thank you for attending today's webinar titled When and How to Use Chl-Scan in OIM Analysis 8. Before we begin, I'd like to cover a couple housekeeping items. At the bottom of your audience console are the application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and you can submit your question. I try to answer these during the webcast, but if a bigger answer is needed, I'll try to email you guys the answer. A copy of the slide deck and some links to additional marketing materials are going to be found in the resource list, which looks like the little green folder. You can also expand the slide area by clicking on it to maximize the icon, top right, or by dragging it out the bottom right corner. If you have any technical difficulties, please click on the Help widget. It has a question mark icon and covers common technical issues. An on-demand version of this webcast will be available approximately sometime later today and can be accessed using the same audience link you had used to come to here. And with that, I'll introduce myself. Honestly, by looking at the attendee list, I think most of you guys know who I am. I'm Sean Wallace. I joined EDAX in 2015 as an applications engineer, specializing in eBSD, rapidly learning a lot more about EDS. I got a strong background in instrumentation in general. My background is focused on things like microprobe analysis, unit CT work, of course in eBSD, all kinds of mass spectrometry also. I've been teaching researchers of all levels for most of my career, from postdocs to undergrads, how to use these instruments. This is why I love my job. I earned my MS in geology from the University of South Carolina and went to work at the American Museum of Natural History after that in New York City as a scientific assistant, where I studied basically the beginnings of the solar system using EBSD on meteorites. So with that, if I'm not here working hard, I'm usually out in the nature trying to find new samples when I'm out hiking. So with that, we'll go ahead and kind of start into the nuts and bolts of this webinar, which is some of the new features we've added into OIM analysis. In this case, when and how to use Chl-Scan and all the fun tools we have built in with that. So first question, of course, is what is Chl-Scan? We've had Chl-Scan for quite a long time. Essentially, it stands for chemistry-assisted indexing. So it's where I'm able to essentially filter the data to help me increase my indexing success rates by using some sort of signal as a filter. Originally, that filter was just going to be your chemistry data, but now that we have it inside OIM analysis, we're able to add things like Prius and IQ and different signals in general. And we'll talk about that kind of stuff as we go along. So again, it just basically is acting as an initial filter to help indexing when I need it, which of course leads to the question is, when do I need it? And when I need it is going to be when these traditional indexing methods fail. Now, the most common one of this is going to be if essentially one or more materials in my sample have very similar lattice parameters. So often I can have a sample that is, has here's a good case, just like austenite and copper. If I look at them, they both have the same symmetry, both have the same crystal system, and I start looking at things like the D-spacing, I can see that they're very similar. In this case here, I got 2.1 versus 2.08 for the one -1 reflector. If I go down even further to lower reflectors, they're still very close. So the 1, -3, -1 has got a D-spacing of 1.1. This is 1.08. In the end, what this means is there's very small differences in patterns. And when you take those kind of patterns, run them through the Huff, there's really no differences that you can see when you're doing this kind of work. So these essentially are to any system going to be essentially the same exact pattern. And because of that, there's no differentiation. So there's no differentiation in my map. So it's kind of just, who's going to win, essentially a coin flip. And that's not going to, give you any good data. It's going to give you very speckled data. You see that kind of stuff in your data. When I go back to this previous slide, when we see this this blue speckled area, blue yellow speckles, this is telling me that I'm having some sort of issue where I'm basically flipping between two different solutions. And because of that, this is going to be one of those common issues with Chl-Scan. And in this case here is going to be the austenite copper, and that's going to be our example later on. So the other good time to use this is going to be geological samples in general. I usually find it's relatively useful to use in multi-phase materials like this. The reason why is in geological samples you have 4 or 5 phases, and it's just a little bit more difficult to index geological materials. So that little bit of help by using the chemistry can really make a big difference in your data quality. So for most multi-phase geological samples, if I see any real kind of issues with what I'm seeing as indexing, I'll just run it through Chl-Scan and say, okay, is it going to have any big changes in my data quality? Now sometimes geological samples, they run fine, so you have your data good at your first shot, but it's always a good practice in general to at least have your chemistry data saved with your geological data to make sure that you can run Chl-Scan. The other kind of a common way, a common time to use Chl-Scan is going to be when orientation effects cause ambiguous indexing. Here's a good example between alumina and titanium. And here in the middle, let's go ahead and we'll talk about this. So we can see in this little diagram down here in the circle, and basically the pole figure, we can see that we have blue areas and we have red areas. These blue areas essentially saying that at this orientation, I cannot really tell any difference between my alumina and my titanium. This is just an orientation effect that we can sometimes see when we're looking at this. Now, this is one of those tools where I think most of our users don't quite fully understand that it's even in the system. So a quick aside on this. So we can see we have this little triangle thingy down here inside of our pole figure. And again, it's telling us how well I can differentiate 2 phases based on their orientations. And again, here in these red areas, I can see that I'm having issues. So one of the features that's built inside of TEAM is the ability to essentially model this. So if I have my phases loaded in my profile, if I go to the simulation tab, I can essentially simulate how well I can differentiate these two phases by essentially just understanding the entirety of the phase space. And in this case, we show it as a pole figure diagram. So what we're looking at here is how easily I can how I can make certain changes in the HUF to pull different data apart. So here in this case, I have a ferrite phase and a different phase beside the ferrite, and I'm wondering how well I can tell these two apart. So in the first one, I'm only using 4 bands. Now, usually you wouldn't use 4 bands, but I'm kind of doing this just to show you guys an example. So in this case, between the ferrite and the other phase, 4 bands really doesn't differentiate. Now, in the bottom one, I've upped the amount of bands to 10. And because of that, I can see I'm getting much higher differentiation between the phases. So anytime you have this kind of issue, there may be even pseudosymmetry issues, or just kind of wondering why I'm having issues indexing, it might be a good thing to go into the Simulations tab, open it up, and just look at how you can see this and see if it's an orientation effect. Now, when this really comes into matter is if you have a textured sample with 2 different phases in it, where essentially you can get in these areas of the pole figure, or phase space, and orientation space, that essentially says, hey, I really can't differentiate these based just on the orientations. And again, sometimes it can be relatively severe. Kind of a niche problem, but again, this is one of those tools that I think is definitely nice to have. And really what this is telling you is, again, they're kind of, the colors of this are telling, again, how well the CI is being separated. So it's just one way of kind of looking at your data to understand why things can be the way they are. So what data do I need to use Chl-Scan? So I need 2 things. One, I need chemistry, which isn't quite true, and I'll get to that. So what I really need is going to be some sort of scalar value data set. I just need something that goes from 0, whatever. And if I have that data set, this gives me that filter where I can choose what I'm using to index. Am I using, the filtering of my data saying, okay, this point has this high chemistry, has a high iron, use my iron phase. My other area has high copper, let me go ahead and use my copper phase. And by far, chemistry is the most common, useful. Now, since we've added this ability now inside of OIM Analysis, we have a couple of different options available to us. In this case, we also have Prius and IQ. So here I have a couple different Prius maps and a couple different IQ maps, and we can see that based on phase difference, on phase, I can see there's a difference in the morphology of these grains, and I can actually use this data now as a differentiation, as a filter to say, okay, what am I doing? So now again, I have to have these scalar values. Now what I also need to reindex is going to either patterns, saved Huff peaks. I have to have some sort of orientation data to reindex on. So in this case here, it's always best to have patterns. If I have patterns, I know inside OIM Analysis I can do a whole bunch more different kind of things with it. I'll talk about that in a minute. But of course, if I just have the saved Huff peaks, smaller in my data sets, et cetera, I can go ahead and use those Huff peaks instead. But I really want to push you to trying to save patterns when you're doing stuff. And the reason why is because, it's always best to start with the best conditions that I have. So I really should be saving patterns in EDS when I want to do this. It gives me way more flexibility in reprocessing the data, including things like NPAR. So I can run NPAR and Chl-Scan at the same time. And that just gives me, again, that way of ability, especially like in geological samples or ceramic multi-phase samples, to say, okay, I have this chemistry, I have, maybe a poor diffracting material. I can include the ability of increasing my pseudo-noise ratio with NPAR, and I can go ahead and use Chl-Scan combined with that now to filter that in chemistry. So this can turn, I've seen, just miraculous data sets where it's like I have no real data to, this is publishable data in a journal just by pushing a couple of buttons. And again, that's why I think it's always best to have both the EDS data and the patterns. Because again, when I'm doing this, I have, the patterns themselves just give me the ability to, have a whole bunch of different options available to me. It gives me the ability to change the number of bands. Especially when I'm dealing with lower symmetry materials, usually best to increase the number of bands. Just gives me, more differentiation in the phase space to really kind of understand what's going on and getting an orientation that's nailed. The other big thing that really is kind of makes the biggest difference in the data sets nowadays is the difference in backgrounds we have built into OIM Analysis. I can do partition-based backgrounds, which means I can take care of some of these issues I run into in multi-phase samples. Things like diffraction strength, maybe slight variations in topography, things like that. These backgrounds really help me get what I need out of my patterns. I just changing these backgrounds. And I think it's an area that I'm going to try to probably do another webinar in the future of just how to use these backgrounds, the effects of these different kind of backgrounds built into OIM Analysis, because it's just very, very powerful. And I think it's one of those things that we need to get out to you guys so that you can really fully start to dive into these more difficult. Because, these tools, you don't need to use these tools on perfect samples, right? So if I have these nice, everything was perfect and just, beautiful patterns and, no orientation effects and all these kind of things, the initial indexing does very, very well. It's really what we're kind of pushing into here is those more difficult and harder samples. Those geologics, those hard ceramics. I've been doing things like graphite and very, very low C materials where I just get perfect data because I have these tools available to me. Now, the other options I also have available to me when I have the patterns is I can fully reset the Huff settings. So it's not just number of bands. I can change my mask, change my spacings. There's just all these different options of going in there that I don't have if I just save the Huff peaks. So whenever I can, I want to make sure I'm saving patterns. Now, there can be this point where, just from a data management perspective, if you have every data set with both EDS and EBSD patterns, you become a data management company by yourself just because of how much data you can do. But again, if you expect you're going to need these options, you should be saving patterns, you should be doing that. So again, the other reasons of why I should be reindexing in OIM analysis in general is because if I have the patterns saved, it gives me a whole bunch of different advantages over reindexing inside of Team. I already mentioned this, but the partition-based backgrounds are a game changer. Sometimes, again, I used to in the past, I have to save that, go to when I'm doing my initial indexing, I got to go, okay, these have way different diffraction strength. I've seen samples before that have pure metal ceramics. So I need to, in that case, back in the day, I would have to optimize my camera to make sure that I'm getting the phase I really need. I mean, there's just so wide a difference there in the Z number that, I'm either oversaturating or undersaturating my camera. Now with NPAR and partition-based backgrounds, that's no longer an issue. The other thing is easy recalibrations. Sometimes your calibration might be a little bit different, or your sample wasn't tilted correctly, and things like that. You're able to basically just push a button and recalibrate your data. Because of that, you can, it just gives you the ability to fix those older data sets that, might have had issues. Also, auto brightness contrast of each pattern. Again, just one of the powerful tools. And of course, if I'm doing a lot of these, I can do both batch reindexing, batch NPAR, and batch Chl-Scan. If I have 10 or 15 of the same things, I can essentially say, okay, run all this information on this data set using either NPAR or Chl-Scan or combined as a batch on 10 or 15 data sets. Incredibly valuable if you're doing 3D data. So, it's just one of those ways, again, I really think that, the power of OIM analysis and reindexing inside of OIM analysis is going to really open up those more difficult samples to be easier to do. I mean, back in the day, if I had a real difficult geological material, it could take me 3 or 4 days just to get, decent patterns consistently out of something. Now with these, I could take those data sets, often first run, and just say, okay, I have all the information I need, and just go ahead with that. So now it's going to be everybody's favorite time. It's going to be poll time. And here I just want to know if you've previously used Chl-Scan and or NPAR. So we just really kind of want to know if you're using these tools that are available to you. So, NPAR is a paid add-on, so I know everybody doesn't have that. But Chl-Scan is relatively, everybody has it. So these two tools combined, again, really kind of start to just give you more and more power. So, it's just a way of giving you, more options of dealing with difficult data sets. I use NPAR quite a bit. People don't send me easy things, right? It's kind of the nature of the job. If everybody sent me steel samples, I'd be very happy, but I tend to get, weird research grade ceramics with 15 phases in it, and NPAR really is just kind of changes how you do things. Let's go ahead and look at our poll results, and I find this pretty interesting, to be honest with you guys, where 61% of you have not used either NPAR or Chl-Scan, which is good because now you're here, you're sitting in this webinar, and you're hearing what the power is of this. So Chl-Scan and NPAR are really kind of important tools in your tool belt that you should be using. And I hope these kind of webinars like this kind of give you guys that idea that, these tools exist and you should be using them. So I wish I could do a poll on the fly, but it'd be really interesting to see why you guys didn't use them, are not using these, either because you didn't know about them or didn't know how to use them. Is it a question of, do you guys not have awareness of these options, or again, just not the training required to use them? And that's where, again, I think these webinars are pretty important. So again, very, very interesting results, guys, and thanks to you for taking part in that poll. So kind of, one of the new things with OIM analysis, we've recently updated and expanded the tutorials to kind of help you guys through these, because we know that they do require a little bit more training than just, push this button, push this button, ta-da, data. So if you go to OIM Analysis, you click on the Help menu, you can see that we have guided tutorials to take you both through Chl-Scan and NPAR. And now, of course, you have this video tutorial where you can listen to it. If you actually have this available on your computer, you can open it up now and follow along. I'm going to be using the tutorial data set built inside of OIM Analysis, again, just so that everything is consistent for you guys. So you essentially have to do these same exact steps as I do them, and then you can say, oh, hey, here I have the same data. So again, I am using the data set inside the Chl-Scan's tutorial, so you can follow along if you do have OIM Analysis. So let's go ahead and get started. So the first thing I have to do when I do anything like this is I have to open the data set. The data sets for our tutorials are going to be saved inside the TechSem folder, inside OIM Analysis 8 underneath samples. I do realize there's probably 2 or 3 on there that if you don't have OIM 8, you're not going to have because I copied them over. But these sample data sets are built in, and again, these are used in the tutorials for you to go ahead and use. Again, it's just a good teaching method in general, especially for new users. I highly, highly suggest you go through all these tutorials. Especially if you have a new user in general to your facility, say, hey, you got a Friday, you don't want to do any real work, right? Go ahead and sit down, do these tutorials, learn, and just add to your knowledge base in general. So again, you just go to File, Open, and then click on the data set. In this case, we're using what's called Interconnect for Chl-Scan. Now, one of the things to notice in this case is there's no actual pattern file with this. So if there's a pattern file with this, it'd be underneath it. It'd be much, much bigger than 26 megabytes. It would be on the order of some of the other guys up here where the pattern files are quite large. But in this case, we're just using a stored HUF data set. So I can't go ahead and really dive into changing the HUF. I can only, in this case, use that HUF that I already have. So the next thing I need to do is I need to open up Reindexing interface. So if I have any sort of map open, in this case, I have an IPF map, if I have a phase map, whatever, it doesn't matter what map I have open. If I have a map open, I want to click up in a little sphere up there with all the lines on it. Go ahead and click on that, and then click on the data set itself. At that point, you'll have a pop-up menu that says, okay, I'm loading up. In this case, you actually can watch it go through it. Now it reads the phase data, it reads the orientation data. In this case, it reads the EDS data. And you can see it also reading the HUF peaks. Now, if I had patterns in this case, it'd be say reading patterns. So again, this just gives me way more data to, again, basically just loading all the data at this point. So now I have the data loaded into memory. The general best practice, I always just make sure it is there. So what I do is I open up my FlexiView option. I click on FlexiView, and I click on Add, and I click on EBSD Pattern Flyby. In this case here, I only have the EDS data. But if I had the patterns, they would show up. In this case here, I can as I zoom over my map, my patterns would show up on the right side. And again, I can see what my patterns look like. Those are going to be raw patterns. So anytime we do this kind of work, we save patterns, we save raw data. We take the basic image off the camera. We don't do any sort of processing on it. We say that, okay, we want that raw data because then I can do different backgrounds on it. If I save it as a background corrected image, I don't have the ability to easily remove that background. So instead, we save it as raw and let you redo a background. Power the backgrounds in OIM Analysis 8. So again, I open up the data. I look at to see if my patterns and EDS data is all there. And that kind of leads to the most important thing. So I go ahead and I open up that interface. In the end, what's going to pop up is going to be this screen here. And this is kind of our reindexing interface. Now, for us, look down there in the bottom corner, I can see this is where my button for Chl-Scan is. So if you mouse over it, it pops it up saying, hey, Chl-Scan. The other thing you're going to see is there's a toggle box there. A toggle box is very important because essentially we have 2 different methods for doing Chl-Scan. One is definitely more user-friendly, and the other one I'm going to kind of touch on a little bit at the end, but not too in-depth. And what we really wanted to be doing here is we want that box to be checked. And that checkbox for PCA. What PCA really is what we call a phase cluster analysis. Essentially what this does is we automatically group and find the phases for you. So we look at your data, we look at the EDS data, look at basic data and say, okay, I'm looking at pixel groups. All these pixels have the same-ish kind of spectra. Because of that, I'm going to call this a phase. So again, it automatically groups and finds these phases for me. On the bottom there, you can see that one that it's copy and pasted 5 times. That's where I do the batch Chl-Scan. If I want to do this on 5 or 10 or 15, or if I have giant data sets, it could be even larger. I can go ahead and do a whole bunch of them at once. Very, very useful if you're doing sets. So now that I have this in a kind of talk a little bit about the phase cluster analysis. So what the phase cluster analysis does is it sends, basically looks at the pixels from the first 4 blocks. It can actually be changeable, and I'll show you that later. So look at the first 4 pixels. I kind of assume them, assume they're all from a phase, and go, okay, now is this, are these similar enough? And if they are, I essentially say, okay, these are reference phase number 1. And look at the next group, and I see how far apart they are from the previous one. Now, this is actually where the Chl-Scan name kind of comes from, because we're using a chi-squared. And what I'm doing here is I'm saying, okay, these are different enough. I can now have phase 1 and phase 2. And what I do is essentially just keep repeating this for that. So now if it matches, I kind of just combine them together and say, okay, here's all one phase. If it doesn't match, again, I define that as my reference phase 2. Again, I just really do complete this for each pixel block in the entire data set. Now, again, we have control over this kind of the block size, and we also have control over what we call tolerance level, and we'll talk a little bit about those in a bit. So in the end, I kind of basically get a map like this. It's saying, okay, I have red pixels, I have yellow pixels, I got brown pixels, I have 3 phases. So when we're done, we're done. And we kind of just match the entire data set after those reference phases. Now again, each pixel is basically saying, you're going to be phase A, you're going to be one of these other phases, and maybe you're phase D. So it's just a way of, again, blocking out the data, filtering it, and saying how many phases I have available. And honestly, if you look at this data, you should be able to look at the EDS data, say, hey, how many phases do I have? And I mean, honestly, that's one of the reasons I think you should look at your data, before you really be doing any of this. So right now I'm going to skip back to an earlier section here and go to this slide. So I mean, this right here, looking at EDS data, I see at least 4 phases. I can quickly just see these just in my oxygen map. I can see this in my aluminum map and my copper map. I have 4 different phases. So I should know that when I go back to this, when my phase cluster analysis is done, in this case, I have 3 phases, but in the other case, I had 4 phases. I should make sure that these kind of match up from what I'm expecting. Now, usually what happens is we do find a couple of smaller different phases, different parts of your sample, because the chemistry is a little bit different. And because of that, usually if you have 4 phases, you're going to have 5 or 6, and we'll talk about how to deal with that. So in the end, this is going to be the window that controls those parameters for the phase cluster analysis. So up there I can see tolerance and average block size. So in this case, the average block size is 4, which is the same one in the tutorial, the one we just showed. Now, the big thing here is that these parameters are what I would call kind of touchy. Here I can see I have 1, 2, 3, 4, 5, 7 total phases. Again, and most of those are going to be minor phases that aren't truly phases. We can combine those, so I'll talk about that in a minute. Now, the tolerance, again, is how well the spectra have to match to be considered a phase. Now, the other one is going to be the block size I talked about 4. Honestly, there's usually no real reason to change that block size. If you change it to be bigger, you tend to miss some phases. If you change it to smaller, you tend to get too many phases. So again, you want to try to keep this block size steady at 4. And this tolerance level can also be really, again, kind of touch it. So don't touch the block size. Again, I've never really found a reason to change it. But the tolerance controls can really kind of, again, overwhelm you with the amount of phases you got. So here's the example I have. Again, I have those 7 phases. I'm with my tolerance at 70. I can tweak it. In this case, I went from 70 to 80, and I've added like 5 new phases. So just, again, an ability to really kind of start to find small things, but often those small things aren't real. So again, I mean, tolerance is usually best kept at around 70-ish. Block size, again, I really wouldn't touch. So again, you don't want to overwhelm yourself with too many. So here we can really kind of see the effects of this. So step back a little bit, and I'll talk about the different windows here since I have them open. So in the top left is kind of our parameters that we can change. So again, we have the tolerance, we have the block sizes, and we have the different maps we're using to do the phase cluster analysis on. Underneath that, you're going to see the chart that shows you the difference between these phases. So those phase colors in that chart match up with the component list on the bottom, and I can see how they vary. On the right is going to be my actual map. Here's where I can match up those colors between the phases that I see. So in this case here, it's relatively simple. You can see that the yellow and the red dominate, and most of the other ones are minor. Now, again, one of the main things of doing this is I have the ability to do the phase cluster analysis on pretty much any scalar map type that I have. So here I can see, I have copper. I've scrolled down so you can't see the iron, but I have iron and copper in this case. I can also use the IQ map, the SCM map, comes off the SCM, or any of my previous options. I also have the ability to use any kind of custom map. Honestly, that might be a beta. I probably won't go ahead and talk about that, but let's just say that you can use pretty much any kind of map you want, including some maps you can bring in. Now, of course, the next thing I have to do is assign these phases. So what I do now is I actually click on the component list in the bottom left, place the red phase. When I click on that red phase, the chart on the top shows me what the average counts, what the average value is for each one of those pixels in the red phase. So in this case, I can see I have iron, I have nickel, and I got a little bit of bleed over copper. That copper is to be an interaction volume effect from the EDS signal. So here I can say, okay, I have iron, a little bit of nickel, be my austenite phase. Now when I originally collected this data, it was originally austenite. So click on that, I can see I have the austenite already saved, and I can just go ahead and click on OK. When I do that, that phase is now selected. So here I go and click on select, pops up that window, and then I go ahead and assign it. Now I have the red phase assigned austenite. Now the other thing to keep in mind here is the little button underneath there that says if no phase is selected, then do not reindex the component's constituent points. I tend to keep that on because here I can see I have that phase 6 at 0.9 or whatever. I mean, it's not going to change any of my conclusions from my map. So I just tend to leave them blank. If they have chemistry similar to one of your other phases you have listed, you can add them there too. So, yeah, again, I usually just kind of keep. Now, in this case here, that copper phase, so here I clicked on phase 2, which I can see is the yellow phase. There's one of those little programmer things. You can see that the red is actually named 0, and of course this phase is actually named 1. But I can go ahead and add that to it. Now, if I'm completely missing a phase, I can go ahead and add it. So here I have my austenite. I know austenite isn't copper-based, so I need to go ahead and add a copper phase. So I go ahead and click on load. When I click on load, I open up my material files. In case I find copper, I can go ahead and add it. Let's see, I actually think I just saw a really kind of a good question. Historically, we have used different sample setups for geometries for EBSD and EDS, especially for quantitative EDS. How good is simultaneous data collection? I assume this is all done with EBSD tilted geometry. Now, this is, again, a very good question. Anytime we're doing EBSD data collection, we're doing it on a tilt. So if I'm doing all this data tilted, how does that really affect my EDS signal? Now, main thing is going to be that it does kind of change the basic geometry of your EDS interaction volume. So if I have this EDS interaction volume, in this case with a tilted sample, becomes more of kind of an elongated teardrop. So I can get a little bit of what we call EDS shift in my data. Usually not that big of an issue. Now, the question, of course, would be once talking about quantitative EDS data. Now, usually quantitative EDS data is a little bit tricky to pull out of EBSD maps. The reason is because let's think about signal generation. Now, if I'm doing an EBSD map, I can go up to 1500 frames a second. If I'm collecting at that frame rate, at 100,000 counts, total amount of counts I'm getting per pixel will be relatively small. So I'm not going to have really kind of good quantitative data on a single data point. But I can start grouping things together and then do that. Our quantitative method does account for tilt, because again, you're changing your geometry, you're changing your interaction volume, and because of that, it does change how the quantitative measurements are done. So again, in general, we have to make sure that essentially there's additional complications on our side, but on your side there really shouldn't be any. Besides, of course, the count rate issue. Again, you're just not usually collecting that many counts on a single pixel. And if you ever collect a data set on an EBSD kind of data set, you can click on it, and you actually get a single pixel spectrum. You're going to see that, again, those can be relatively small. So with that, let's go ahead and go to the next step here. So now I've added this phase. I've added the copper phase. I can see that, and I go ahead and add it. And I go ahead and now have those two phases. Now again, for these smaller phases, again, there's a couple real options for kind of getting rid of these. I think the thing you really have to make sure is, I can track down what I would call the real phase. So I can go ahead and click on these secondary phases and see if they exist. Most of the time, are they real? Yeah. So here's an example. I've clicked on the neon green phase, and I can see that I have certain areas that are very high nickel. So I can go ahead and track down that nickel phase, and I can reindex using it. But now let's go ahead and look at the map on the right. Where are those green pixels? I mean, you really can't see them because they're relatively sparse. They're not grouped in any large kind of sort of grain. So it might not be worth adding. Is it really going to tell you anything about your sample? It may or may not. So, if it is, go ahead and find it, track it down, and reindex it. If it doesn't matter, just don't reindex it. And that's, again, you just click on that box down there that says, if this phase no phase is selected, don't reindex it. Again, anytime you're doing any sort of this kind of work in this reprocessing, always think about what the end goal of your data set is. Because this is one of those really kind of important things about EBSD, is I can change my thing. So there's different ways of dealing with data sets, and in the end, again, my end goal should always be there. Just again, one of those things like of feeling with and going with different data sets. So with that, we're able to again either add the phase or not add the phase, and because of that, I can go ahead and it's time to start. Now, the way to start is going to be the bottom right, there's a little go button down there, and you basically just click on the go button, and it goes. So again, what this is doing now is it's saying, I'm taking out that pixel, I'm looking at that pixel, I'm saying, I have assigned this to the yellow phase copper. With that copper phase, I can go ahead and now say, go to reindex that. Now I'm reindexing that point, in this case based off the HUF. With that HUF settings, I said, okay, with these HUF settings and these bands, only look at this phase, use this phase, and then go ahead and reindex it. So now I'm able to go, okay, here's this orientation. I no longer have any complications from any other different phases, so I'm getting better indexing quality, and with that in the end, better data. So I go ahead and press go, and we start to index. Now the other thing to keep it down here is the component map. Essentially there, it just turns off the overlay, so I can see the grain structure underneath that. So if I went and clicked off the component map checkbox, in this case, I would see the IQ map underneath it. Again, it's a different way of doing that. And I actually can change that grayscale map by using the pull down on the right. Again, it's just different ways of actually physically looking at yourself. So now if I go ahead and click on that, we can see that we get our reindexing. So if you saw my webinar on NPAR, this should look familiar. You can see that on the left there, I have my indexing results. So I'm actually watching the IPF map build up. The bar right to the right of that image with the little green thing on top is going to be my IQ through time. So essentially, I can see how my IQ changes from top to bottom. And again, it's just useful, again, especially if your signal changes. I find it really useful for like tungsten-based scopes. Again, if some of my beam condition changes, I can usually kind of see it in the IQ too. But again, in this case, it's green. Good. Yellow starts to mean meh. Red means I should probably look at why it's red. On the bottom right, I can see different data there. Now, we're all good with the data. We can look at it in the bottom right. And here I can see I have displayed patterns on. With the display patterns, in this case, it's just showing me the HUF. If I was running NPAR and different backgrounds and actual patterns themselves, then it's a different kind of different thing. I would actually be seeing those patterns themselves with the background corrected over the NPAR on it. And it's just beautiful sometimes, those NPAR patterns. I can also turn on the crystal display so I can watch it flip back and forth. I can also see my display stats. Now, display stats in this case is going to show things like time remaining, points remaining, row average CI, just a little bit more information so you can understand what it's doing while it's running. I usually keep it on display stats just so I can see how my indexing results are going to give me an actual number. In this case, when you look at it, I think the average CIs are going to be on the average of like 80, 90. Then I can see different things. So that's why the bar is green, because I'm getting really good indexing. So here again, I can see as it continues down, the green bar fills in. With that green bar filling in, I'm very, very happy with my data, and I can see the IPF map is going on. Now, I get asked this question quite a bit, so I'll just kind of tell you. You can see that it looks a little bit blocky in there. That's just a pixel resolution to pixel resolution thing. We are taking a hexagonal grid. You're putting onto basically a smaller pixel size on your computer, and also by shrinking it. So that's just kind of an artifact there. So that blockiness you see is not your data. In this case, it's just it's a display kind of issue from going all these different things. So not too just a way again of. So in the end, what happens is you get a new data set. So when the data is done, what happens is it makes a new node over in the project tree. And what we name it for is basically, we just put a rescan after it. Same thing with NPAR. So it has the initial name and then rescan. You should always rename your data. I do this all the time to myself. I click on it, and what happens, I do a new data set, data set. Suddenly I have 10 data sets open, and I have no idea what I did to them. So you should go back and rename them as a best practice. Again, I fail that all the time, but again, it is a best practice. Now, what I can see here is my actual final data. So in this case here, I have a phase map, and I have an auto IPF map. Now, if you remember, if you go back to the original maps we looked at, I only had the austenite phase listed, but I didn't actually have a phase map when I first did this. Because it's only one phase. So it'll be like, woohoo, it's all one single block. Now that I have two phases, I can see where those phases are differentiated. I would not have been able to do this again alone without the chemistry data, because I just don't have that information available to me to differentiate the patterns of these two phases without it. So in this case, again, the lattice parameters are also. On the right is going to be my IPF map. Honestly, in this case, there's no real change to my IPF map because the lattice parameters are so much the same. There'll be slight variations, but very, very little. In the end, we have our done map, and that's kind of our goal here. Is I now have usable data that I can say, okay, these phases are better differentiated because of copy. Now, here is where we kind of talk slightly about the other method. Actually, it looks like I would have had a little bit more time than I thought, and I could have probably expanded on this. So I'll go ahead and talk a little bit about this. So if I didn't check that box, that little PCA box to do the phase cluster analysis, what happens? What happens then is I go into the manual Chl-Scan mode. And this manual Chl-Scan mode really gives me the ability to, again, do this all by myself and give me a little bit higher, just gives me more control of exactly what's going on. So here I can see on the top left I have the austenite phase. If I pull down the pull down menu, I have the copper phase. And on the bottom, I can see the different kinds of maps have available to me. So in this case here, I have iron, I have nickel, I have copper, and I also have the IQ and the SEM image. I can actually use the pull-down menus up there again, and I can change those. So I have 5 maps available to view at any time. Now, the maps that you're seeing there, the square ones, those are just a signal done in a histogram form. So here I can see on the left, I have my iron map, and the blue is going to be low iron, middle, high iron. Now, those kind of give me an idea how many phases I have. Underneath that, you're going to see the histogram. But again, on the left, it's color-coded, so the blue is going to be the low. And as I go to the right, I can see, that I have a higher phase area, a higher count area of my iron map. You also can see those 2 bars. Those 2 bars define the area where I'm basically thresholding this data. In this case here, I've thresholded that data, and I say, okay, here's my lower limit, here's my upper limit. These pixels I want to include. And I can do that for each one of these maps. Now I'm saying, okay, these irons in this area included. Then I go to my second filter. In this case, it's my nickel. I would move those bars and say, okay, only do this area in the green for the nickel. And I go to the next one for my copper, and I can change those. Say, okay, where do I want these? In this case, during the austenite phase, I don't want to include the high copper areas. So I choose the low copper areas, so I just have those blue areas. And I can do the same thing with the IQ or the other maps. If I don't move the bars, I don't include them. So in this case, in the IQ map and the SEM map, I'm like, I don't care about you. I don't want to use you as a factor. And because of that, I'm not going to move my bars. In the end, what you can see up here is you're going to get a point within the channel limits box up on the top middle there. In this case here, I can see the red ones. Now in this case, I can actually look at it. I can see it speckly. I'm missing some areas that I don't want to miss. So I'll have to go back, change those threshold bars, and essentially go ahead and increase the area that I'm including in the austenite phase. Again, it's just a way of doing it. And I click on the Go button, and I go at it. And here we can see kind of the manual selection of those limits, where I just kind of zoom in at it and go, okay, here's what's going on. Here's that area. Here's my map on the right. So again, it's just a different way of really kind of going into and manually selecting the limits if you think you can do a better job. Sometimes you can do a better job than the automatic way. Sometimes you can't. Again, it's just one of those things to really kind of play with and see if you can do a better job. I mean, it's just like the camera optimization settings. Those camera optimization settings, you can push a button and it automatically optimizes the camera for you. Sometimes it works great, but oftentimes I find I can do slightly better because I'm used to dealing with it. Same thing goes with Chl-Scan. You have the ability to use the optimize button, go ahead and get done with it, and in the end just say, hey, ta-da, we're good. But sometimes it fails or just doesn't do quite the job you want. You can go ahead and tweak the settings, or you can go ahead and do it manually by again unclicking the box. So with that, I'm just going to talk a little bit about our additional resources. We have, of course, our blog and our webinars. Again, our webinars are awesome. I suggest going back and looking at them. They're just an amazing tool. And with that, we're really kind of able to, do different, different kinds of things. And just again, it's a tool for you, so that we, after the sale, you have the system, go ahead and really kind of learn how to use that. And with that, I really kind of open up the floor to any additional questions. Let me go ahead and look at see what we have here for questions. So I have an old question here talking about data management. So the question is for data management, can you go ahead and save and export your pattern data as zip folders the same way you can save and export your EDS data in a compressed format? The answer to that is yes. Whenever you do this, you can basically click on the data set and go ahead and export it. You can see it says include export, or it says include patterns in file. And that go ahead and includes the patterns. And it also says, the button underneath there says delete patterns on export. So you're able to both save the patterns, export them into the zip file, and then also delete them on that. Again, I mean, amount of data we do, it can really kind of grow out of control and very, very fast. Because, you're saving images, and if you're doing large maps, you're saving a lot of images. And there really is just no quick way of kind of saving data. Let's see, additional questions. So we have another question here. It says, if the experimental setup does not have the ability to do EDS, is it still possible to run Chl-Scan without the elemental maps? What would this do to the results of the Chl-Scan? The answer to that is of course, EDS would be the best way to do that. But what you really kind of want to do in this case, and again, if you have the EDS data, it would be best. But in this case, you do have things like the IQ map. IQ map can be useful. I've seen it done before with like Martensite fair right issues. So again, there EDS doesn't that big of a difference, but the IQ map does. The IQs are just way different than what you're looking at. Same thing with Prius. I haven't really fiddled with Prius all that much, but you really kind of start to see major differences in some materials on the diffraction strengths and on their orientation effects. And because of that, the Prius top, Prius center, or Prius bottom can really give you different views of the data, and you can threshold that. So if you go back to, see if I can find the slide real quick. That's going to be this slide. Go ahead and bring the slide back up. So here you can see that box up top here where I have the copper and I have the IQ and all these. I can, again, if I didn't have the copper, I can click on the IQ or one of the Prius images. Or I also use that custom button. And that custom button lets me use different data sets. So I can build my own custom data set if I wanted to and use that instead to assign the phase. So yes, I am able to use that. But the question really is going to be in the end is this value giving me enough separation between these phases that I can, use these as a map. And sometimes you just don't have that. So yes, it can be done if you don't have the EDS data. But the question really could be is do these other maps differentiate between the phases strong enough to really kind of do it? So with that, are there any more questions? Let me know, and we'll go ahead and answer it. If not, we're going to be kind of done here. So looks like with that, guys, we're going to wrap this up. Really grateful for you guys to be there. I'm very happy to see these tutorial videos are getting very well attended. And again, it's just a way of us giving you guys more information, a little bit more training of how to use these functions and get better data out of them. So thank you guys for coming, and it's been nice sharing this information with you.